So let's talk about what antiderivatives are. I'll start with this. You don't even have to look at the page there for a minute. Addition, you learned, and then subtraction, right? Elementary. You did multiplication, then division. You at one point did squaring a number, and then you learned square root. Even trig, you would do sine, right? Sine of a number, but then to solve and work backwards, you did inverse sine. So basically, every operation you do has an inverse. Naturally, we've been doing derivatives, so it has to have an inverse as well. And we're very clever with the name antiderivative. So, yeah, makes you think we could have just called it subtraction, anti-addition, and then anti-multiplication.
Yeah.
So, would that have helped you learn it better? Probably. So that's what we'll be doing. That's the concept of antiderivative, is simply undoing what a derivative was. Let's see if there's anything else I want to say here. So function, yeah, usually we're going to say, I did something a little different here, but if you see capital F, so if your original function was f, capital letter means it's the antiderivative of that function. So therefore, here in the other direction, if you did the derivative of your antiderivative, it would take you back to the original function. Just as if you squared the square root of 4, it would take you back to 4 instead of 2, then it would be 2 squared, which is 4. So you might ever say antidifferentiation, just as differentiation was finding a derivative. Antidifferentiation is finding an antiderivative. Let's see, inverses. Last thing I'll say before we try some, I say, just as like the first one was a little bit easier at first, right? Multiplication, a little easier at first, and then division.
Sure.
But now you probably got it. Same with, I'd say even square root, because sometimes, I don't know, like that might have been harder to think of at first than just squaring a number, right? 8 times 8. So this process at first might be a little bit, like it just takes a little practice, but might be a little bit harder at first, but once you get used to it, it'll be just as natural as finding a derivative. And let me say this, there's actually many processes that will get antiderivatives. But at first, we just do some of the basic ones. So, all right, here we go. So find an antiderivative for these functions. So I'm going to try I'm going to try the first one with you, because then I want you to try a few others. We're just going to go through G. Okay, so just through G. So for example, we'll just start with A, and then you try and think of some. Find an antiderivative for the function. So this is f prime being 2. So we want what the original function would be. And most of these for now, you just got to think backwards. So really ask yourself, what function would have the derivative be 2?
2x.
So perhaps 2x. Right, couldn't that be the antiderivative? Because the derivative of that would get you back to 2. So that's what you got to think. Whatever you put here, well then when you take the derivative of this, it must be there. Okay, it must be back to the original of 2. I'll go ahead and tackle something at the bottom. Can I think of another function that would have worked here? Oh yeah, there's actually an infinite number more.
So like 2x plus 1.
Very nice. 2x plus 1. Wouldn't that derivative also be 2? You're like, oh yeah. Another one? 2x plus 100. Yes. 100 would also work.
2x plus 1,000.
Okay.
2x plus 1,000,000.
Thank you. Yeah. So. So basically, there's a theorem I'm actually going to talk about in a minute more fully, but that's basically one of the important theorems is there's actually an infinite number of antiderivatives for any function because you could always put a constant there. because then the derivative, this would go away, it'd be 0. But this would still be 2. Okay, so why don't you take a few minutes and try out thinking through the antiderivatives through G. So again, good work out there. Let's do a review. I'll just go in order. I actually think B is one of the harder ones from A through G. Anybody think of what could be an antiderivative for part B? This is from Unit 4. You guys got it right. The back. You guys got this.
ln of x minus 1.
ln of x minus 1 because, thank you, because the derivative of ln is 1 over x. Remember that? Derivative of natural log x, the derivative is 1 over x. So this one we had to put in x minus 1 just because the bottom was x minus 1. It technically has a many chain rule with that, but it's 1, so. So the derivative of this is 1 over x minus 1. That's why this is the antiderivative, working backwards. How about C? Many that work here. Anybody? Yeah?
I just said all real numbers.
Okay. So any number. Is that right?
Yeah, it's a good number.
But yes, you could just make a note. Any number. So the antiderivative of 0 is any number. I chose 4. Now really what we can put, well, see I bet on mine I just said any constant. Yeah. We're going to write that as well. I put C, any constant. We're going to use that in a minute to represent any number. So 4, C, if you wrote any number, that's fine. All right, so this is good. Let's do a polynomial one. So we can do this one in parts. I have to use S here. So what's the antiderivative just of the first part, 9s squared? You got it?
3s.
Nice, yeah, 3s to the third. Now, is there a way you thought about that, or did you just kind of guess and check, or?
I guess and check. It just
Check both.
is, because 3 times 3 is 9, and
Mhm.
I'll have to take it down 1.
Yeah. Yeah, so exactly right. So this here, the degree is already down 1, right, from the antiderivative. So here the degree had to go up 1. So normally, I mean, for power rule and polynomials, doing a derivative takes the degree down 1, but an antiderivative takes the degree up 1, since you're going backwards. Yeah, and then I like what you said. You just thought through really like this number times something would give you 9, and it's 3. Do you guys think similarly about that? Just kind of on that track. But again, the degree must go up 1. So for example, on the next one here, it's really to the first power, right? X to the first. So what was the second part?
S squared.
It's just s squared because really there's a 1 here, and so you'd say, well, 2 times what number would be 2? It's just the 1. So you know their coefficient needed there. What about minus 3? Similar to part A. It's just minus 3s. So if you're starting to see some patterns, which we're gonna review the general strategy for all these in a minute, but for this one, hopefully you saw that the pattern up here. If there's just a number, the antiderivative is just add x or add s. That's it. What about, so good, any thoughts so far? That's seen a couple polynomials. What about E? When you think of the function, when you do the derivative, it's 2e to the 2x. Yes?
I got e to 2x.
E to 2x, yeah. Because if you remember from Unit 4, some of these take us back, no power rule, no product rule, but just some of the Unit 4 ones. The derivative of e to the x is e to the x. But this one, for e to the 2x, we need a chain rule. So it was times 2x. Times the derivative of 2x, excuse me, which is 2. So the derivative of this is 2 e to the 2x. Yeah, so if you see an e in there, e to the x type exponential, it's going to be itself in there somewhere. So that's got to be in there. Very nice. Here's another power rule, type 1. It's slightly different, especially on the second part. So, what did you get for negative 3x squared? Negative x cubed, yeah, again. So the derivative's got to go up 1 to 3, and then you're thinking 3 times what number would be negative 3? And it's negative 1. So no other coefficient needed. Again, all of these, check them. The derivative of this is negative 3x squared. That might be what you're thinking as well. Just somebody might say, all right, in your mind, what function could I write down so the derivative is negative 3x squared? So the next one, plus, so I've talked about the degree's got to go up 1. What's the coefficient here? What's the rest? 1/5. No, we could write x to the 5th over 5. Very nice. Because again, you got to say 5, power rule, 5 times what number would give me 1? Yeah, it's 1/5. So that one, the first one that I think is up there is fractional for you. Okay, nice. Let's do one more that you guys worked on. So last one here is, again, a unit 4 one, recognizing a to the x type. So anybody got this one? Antiderivative? Yeah? Just 4 to the x. Because the derivative of a to the x, a number to the x power, is itself. Derivative of this is itself, 4 to the x, ln of the base, which is 4. And then there's no chain rule in this one. X is 1. I'm sorry, the derivative is just x. And so the exponent is x. The derivative would be 1 out there. It's Monday. Okay, so I'm not going to do I. This is actually more kind of, you'd have to think of the product rule on this one. But I do want to do H. I don't think, did I have any other trig ones? No, I didn't have any trig ones. Well, I would have been. So I know I didn't have you do this one. Any thoughts on this one? So you got to think backwards from secant squared. So the original function that had the derivative would be secant squared. Then tangent, yeah. Tangent of 4x. So the derivative of tangent 4x is secant squared 4x. Chain rule times 4. That's what we have there. So, see, you see different types.
So what's the answer?
This one. I'm just showing you, like, if you work through and did the derivative. All these are nice that you can check by doing the derivative. What was I going to say? So you've seen a general array of these, not every single one yet. For example, we haven't seen a sine or cosine one, but we've seen a decent amount in the process. Any general thoughts on those right now? Okay, I'm going to show you a summary of them in a second, what they generally are. Let me talk about a few things. One is we're going to start to see this. I think I put it on. I certainly put it on the practice. I don't do it on the next page yet, but I put it on the practice. I'm going to start using this. So the process of finding an antiderivative. This is the title of the unit. Integration is actually, and this symbol is the integral sign. There's actually two meanings to it, but for now we're just looking at one meaning of it, which means find an antiderivative. So again, the title of the unit, integrals. The process of that is integration. This is the symbol for integration, like that. So for now, it's going to have two meanings later on, but for now it just means find the antiderivative of that function. So all of these up here, I could have, instead of this, I could have just had this. And that means find the antiderivative. So it's standard notation. This is also called the indefinite integral because soon, later in the unit, we might have numbers here and here. So that would be a definite integral. But for now, it's the indefinite integral. You can just say the integral sign if you want. So we found out it's reversing a lot of the derivative formulas. And I'll have a table on the next page that summarizes this. Okay, and last thing before we look at that is what we already saw above. This theorem, functions with the same derivative differ by a constant. So it says if f prime equals g prime, so if two functions have the same derivative, then there is a constant such that f of x equals g of x for all values in that interval. So here's an example, and I'll show you above as well. All of these functions have the same derivative. 2x for each of them, right, is the derivative. So they all differ by a constant. This constant is 0, this one's 1, this one's -3. So if functions have the same derivative, the original function will differ by a constant. So that's what that says. So the only difference in the original function was the number at the end. All right, so like again, for our purposes, I set it up here. We could have added any number to any of these, even at the end here, plus 10 or something. Any of them would be an antiderivative. If you just add a constant, because when you do the derivative to check, that would be 0. All these would be 0. Okay. I think we're ready to flip the page. Let's go ahead and flip it. So on the next page, I sum up. You might say like, you might be doing okay with some of those. Guess and check on some. But there are actually, just as there was derivative formulas, there are some antiderivative formulas that help simplify. So let's look at this table. I'll try and give you some examples as we go through, but let's look at what this means. So these are general antiderivative formulas. All right, so the first thing is all these have this symbol now. So that means find the antiderivative. Then you're going to start seeing this after they list the function. For example, sine x. They're going to have dx or dy or dA. All that's telling you is the variable. So let me, what was the first one we did here? 2. So if my function is 2, and it said find the antiderivative of 2, I'm doing the part A on the last page. Antiderivative of 2, and it said dx, the answer would be 2x. But if it said 2, the antiderivative of 2 dy, then the answer is 2y. It's just the variable. It's just telling you what variable to integrate. So if it said dc, then the answer would be 2c. Just the variable. That's all it is. So that dx has nothing to do with like impacting the actual function. Okay, it's just there as a guide telling you what variable. All right, so let's look at the first one. This was k. This is just a number. So it was just like, yeah, a, like 2. So if it was 2, we said the antiderivative is 2x. Now the other thing on all of these is you'll see plus c. So what that does is it tackles the fact that there could be any number. So here I said 1, or it could have been 10, or 1,000, or 20. So what we're going to start doing is write plus c, any constant. Okay, the next one. This right here, it's an important one. This is the antiderivative power rule. Okay, so let's see, the original power rule for derivatives was n x to the n minus 1. So you do the derivative, we take the exponent down and then subtract 1 from the power. Okay, that was the rule, in case you're wondering, for derivatives. This is the power rule, but for antiderivatives, so going in the opposite direction. Now, some of you probably just did kind of a guess and check type thing. I'm looking at when you did like 9s squared here. So that's fine if you did guess and check. I'm just telling you there is a formula. So if you want to follow the formula, this will always work. So let's take it if it was like, what was it? 9s squared. First, yeah, okay. Well, here's the thought. All numbers, just as with derivatives, when we're doing the derivative of 3 times sine x or something. Remember how the number just slides down and then we do the derivative of sine? Same here. You can just bring the number outside. So like really I'm just doing the integral of s squared. You can keep it in there if you want. Sometimes it might help if you think of it, but it's the same as derivatives. So then the power rule for antiderivatives is this. X to the n plus 1. So that just means you add 1. So right here. So I'd have the 9 come down, and then I would add 1, s to the third power. Okay, over n plus 1, so n was 2. And so over 2 plus 1, which is 3. Now, at first I do see a lot of people write this. They like to see it, so they write 2 plus 1 over 2 plus 1. That's fine, then they work it out to 2 plus 1 is 3 over 3. So if you're more comfortable doing that, you can. And 9 over 3 is 3. Okay, but that's the power rule, working backwards. So you add 1. This just says, take whatever number the power was, add 1, so it's cubed. And actually, here's what I always do. It's the same number. So whatever you put there, you put on bottom. So like looking back on the last page with that x to the 4th one that Chris did as x to the 1/5, you could also do x to the 4 plus 1, which is 5, and then just put the 5 on bottom. And that's the same as 1/5. So that's an important one. Let me stop and see if there's any questions on the power rule one. Okay, let's look at some trig ones. So the derivative of sine was cosine. So the antiderivative of sine, this is a little opposite, negative cosine. So let's see. Derivative of cosine was negative sine, and so the antiderivative of cosine is actually a positive sine. So this is where sine and cosine, the signs, the negative and positive, they actually switch. And I mean, you can just see it here, like, remember you can check all these by doing the derivative. The derivative of sine is cosine. So those just switch. Like switch signs, but they're still sine. Sine and cosine. Next one, derivative of tangent was secant squared. So this was just like from the front side part h. So the antiderivative of secant squared x is tangent x. Let's see. Secant tangent was the derivative of secant. So the antiderivative of secant tangent is secant. Antiderivative of cosecant squared is negative cotangent. The derivative of cotangent was negative cosecant squared. Again, this is where the sign changes. Same with the sign on this one. The derivative of cosecant was negative cosecant cotangent. So the antiderivative of positive cosecant cotangent is negative cosecant x. Now that's all I have for the trig ones. Now you might say, what's the antiderivative of just tangent or just cosecant? Right, we don't see those. We see like from tangent we got secant squared, but we don't actually just secant up there, right? The antiderivative of secant. Some of these are a lot harder, or we need more processes to do, so we'll learn them later. For example, tangent. We'll learn that one next unit. Yeah. Some of them are just harder to do, harder to find. So integration in general is a little more complex in that you can't always find them. You can't always just use a power rule or a product rule. It doesn't always work. So it's a little more in depth with finding something. Okay, let me talk about the last few here. Any thoughts on the trig ones? No. To finish up, these are some from Unit 4. So derivative of e to the x is e to the x, so antiderivative of e to the x is also e to the x. No one's still the same. Here's, this was part B from the front side. The derivative of natural log x is 1 over x. Therefore, the antiderivative of 1 over x is ln x. With absolute value. We'll see why later on. So do you see how I put the 1 over x? But so it could be like this, but generally we forget about the 1. It's just a placeholder. So we move the dx in there. But you could also write it as 1 over x and then dx. Okay, and then this was part F or G. Antiderivative, well, I had 4x ln 4. So if you have the antiderivative of 4 to the x itself, it's 4 to the x over ln 4. So this time, if you remember, just doing the derivative of this would cause you to really multiply by ln 4. So if you're doing the antiderivative of it, it causes you to divide by ln 4. This one, instead of multiplying, you divide. What's the last one? Okay, so then I put up here in Unit 4 the other key ones that we were doing. Well, Unit 4 was chain rule, so that was 2 functions in 1. We'll do that next unit. But we also had some more complicated, we had ln and log itself, just ln and log. Again, some of these are more complicated. We're not going to do that in this class. I think I actually look later on about ln of x a little bit, but anyways, these will be covered in a different calc class. So what can I answer before we do 2 final examples? Anything I can answer on the rules, the table there? Very good. Okay, so last thing we're going to do is called initial value questions, initial value problems. So if I said, this is one where if I said, all right, here's the derivative of 4x, and I said, well, the antiderivative of 4x, it would be 2x squared, but there would be a constant, okay, plus some constant. Well, if they actually give you, what did I see here? If they actually did give you an initial condition, so they said, well, actually, we knew when x was 0, y was 5. If you actually have a point, f of 0 equals 5, that's 0.05. If you actually had that, then you could actually find what c is. Okay? And that's what we're going to do. So only if they give you an initial condition, then you can actually find what c is. Otherwise, you're going to have to just leave it as c. Right, so that's what I sum up here. So like on this question, they actually found that c was 5. So let's do 2 of those. Oh, the last thing I should say here is it's just find the differential equation. A differential equation is just an equation that starts out with a derivative. Okay, so we're still solving the equation and getting the c value, but a differential equation is simply an equation that has a derivative in it. So we start with this. F prime x equals sine of x. It starts with a derivative. Solve it for f of x, and then with the given initial condition. So we'll actually find c. Okay, so just as you know, sometimes do the derivative of each side or do ddt. Used to do that to both sides. I'm going to do the integral, the antiderivative to both sides. So I can take the derivative of both sides, I can do the integral. So on the left side, the antiderivative of a derivative just takes us back to the original function. Right, those really, they really just cancel each other out. And on the right side, we can do the antiderivative. So somebody help me out. The antiderivative of sine. Yeah, normally it would be, derivative would be positive cosine, so just antiderivative. Anything else? Plus C. Yeah, so get used to that. For all these to start, you're going to be writing a lot of plus C. Yeah, don't forget that, because it could be any number. So what we note is actually our function goes through this point, 2, 3. So that's part of f, the actual function. And so all I'm going to do is I'm going to plug in my x value. Oh, I have 0, 2. You have 0, 2? I don't know why. I must have changed it, sorry. Okay. So our function passes through 0, 2. So what I can do is plug in 0 for x, 2 for y, or f of x, which is y. And then I can solve for c. So I just did a substitution there, plugged in 0 and 2, and I can evaluate. So negative cosine of 0 is the x coordinate here, which is 1 at the start. So it's negative 1, and then plus c, and we'll add 1. So we'll get 3. And then write your final equation for f of x. It was negative cosine x, and then c is now 3. Is that fun?
So fun.
Finding the antiderivative is fun in itself, but then actually getting the c value, very satisfying.
Put it all together.
Just so satisfying.
It is, because I don't know. C could be any number. What is it? You know,
Measure line.
exactly.
Drawing lines through them to make them look like pointers.
You got anything fun this weekend?
I can't stop thinking about it.
No.
I went to the basketball game on Friday. Girls, how'd you guys do?
One.
They ball it out.
Orange.
What was it?
It's not Pacers.
50 to 39, I think.
The school colors aren't changing.
Not too much else. Got a little drums this weekend.
You play the drums?
Watch the Mavs.
I'd say that.
Nah.
Like
I didn't know that.
Good
I
basketball.
thought you played the guitar or something.
All right, so let's finish this up. So let's do another one. Now this one, they give us 2 initial conditions. This is x and y. This is the slope, the derivative x and y. At 4, the slope is 0, derivatives. And we start with the second derivative. So we have to work backwards twice. Okay? Because they want f. So I'll do the antiderivative of my second derivative. So this will take me back to f prime. We go with that. Second derivative, if I do an antiderivative, take me back to first derivative. So then this was part A, the very first one. Antiderivative of 2, 2x
Plus C.
plus c. So I'm going to first, so sometimes students on these want to do an antiderivative now to get back to f. Well, we need to get c first. So, that's a great idea, but we first need to get c, then we'll get to that. So here's the derivative initial condition. So I'm going to plug in 4 for x and 0 for f prime of x. So this will be 8, and so we'll get negative 8 for c.
Can you slow down?
What did you use for? Oh, got you.
The 4, I plugged in this is the x value for derivative, that's the y value for the derivative.
No.
Yeah. Well, this I was just kind of working out a subtracting. So now I'm just plugging in negative 8 for c. All right, and now I will do the that's pretty much where I had last time on part A. But for this one, I need to get back to the original function, so I'm going to do it again. So the antiderivative, I'm doing the integral to both sides, which is finding the antiderivative. So the antiderivative of the derivative is just the original. Takes us back to f. Okay, then over here, I can do power rule. I think we also solved this one. The antiderivative of 2x is x squared. If you want me to do power rule, it would be bring the 2 down, then add 1 to this. Right, so it'd be x to the 2 over 2. So when I do the power rule, I keep whatever number I add 1 to, 2 and 2. And then the 2's cancel. That might be one, though, where you just think, I know the derivative of x squared is 2x. So going backwards, it's just x squared. And then antiderivative 8 is 8, oh, negative 8 is negative 8x plus c. Plus c. Okay. So now I need f, but no c, so I'm going to solve for c. And my x is 4. And my y value is negative 1. So let's just work it out. 4 squared is 16. Negative 8 times 4 is negative 32. 16 minus 32 is negative 16. Finally, I'll add 16. So that's the one that cancels. So negative 1 plus 16 will get 15. Okay, and don't forget, sometimes don't forget they forget to write the final. So write the final. It was what was it? X squared minus filling in c. X squared minus 8x